The transition elements have an unparalleled tendency to form coordination compounds or complex compounds. Complex compounds are those in which a central atom or ion is surrounded by a number of anions or neutral molecules possessing a lone pair of electrons. These surrounding anions or molecules are called ligands. Some examples of complex compounds are given here. They are pentamine cobalt 3 chloride, potassium ferricyanide 2 and nickel tetracarbonyl 0. The tendency of the transition metal ions to form complexes is due to their relatively small size and resultant high positive charge density. Presence of vacant n-1d orbitals. Their ability to show multiple oxidation states. Now let us look at the catalytic properties of these elements. Transition metals and their compounds are known to catalyze various reactions of industrial importance. The catalytic activity of these elements is attributed to their ability to exist in multiple oxidation states, which enables them to form unstable intermediate compounds. These metals also catalyze reactions by providing a suitable reaction surface. Familiar examples include the use of vanadium 5 oxide in the manufacture of sulfuric acid by the contact process. The use of finely divided iron in Haber's process for the manufacture of ammonia, and the use of nickel in the hydrogenation of oils. The table here shows the catalytic activity of some of the transition metals. Many views have been advanced to explain the mechanism of catalysis. In catalysis at a solid surface, bonds would be formed between the molecules of the reactants and the surface atoms of the catalyst. The 3d electrons of the first transition series elements are used in bonding, in addition to the 4s electrons. Thus, the concentration of the reactants at the catalyst surface increases, and the bonds of the reactant molecules weaken because their activation energy is lowered. Since the transition metal ions can change their oxidation states, they act as catalysts more effectively. For example, iron 3 catalyzes the reaction between iodide and persulfate ions by changing its oxidation state. It first gets reduced to Fe+2 by oxidizing iodide ions, and then gets oxidized to Fe+3 by reducing persulfate ions. Now let's look at the formation of interstitial compounds by these elements. Interstitial compounds are compounds of indefinite structure and composition. They are formed by the incorporation of small atoms like hydrogen, boron, carbon, or nitrogen in the spaces between the metal atoms, that is, the interstices of the lattice. The component elements of these compounds do not combine in definite ratios. Hence, these substances are also known as non-stoichiometric substances. For example, Fe0.940, TiC, Mn4n, Fe3H, VH0.56 and TiH1.7. Note that the formulae do not correspond to any normal oxidation state of the metal. The important physical and chemical characteristics of these compounds are: they are extremely hard. Some borides approach diamond in hardness. They have higher melting points than those of pure metals. For example, titanium carbide melts at 3683 Kelvin and titanium nitride melts at 3473 Kelvin. They are chemically inert. They possess good electrical conductivity. Let's look at the alloy formation by these elements. Pure metals have poor mechanical properties. Hence, they are not used as such in industry. The properties of the metals may be modified by adding other elements. Alloys are one such class of compounds. An alloy may be defined as a homogeneous mixture of a metal with other metals or metalloids, and sometimes even a non-metal. The atomic radii of the transition elements in any series are not too different from each other. As a result, they can very easily replace each other in the lattice, and thus readily form alloys. Alloys are classified according to the components in two distinct types, namely, ferrous and non-ferrous. Ferrous alloys contain iron, carbon, and one or two of the other elements like chromium, vanadium, tungsten, and molybdenum. When the content of carbon in an alloy is less than 0.1%, it is called an iron alloy. When the content of carbon is more than 0.1%, the alloy is called a steel. Depending upon the other elements present, steels are classified into several types, like vanadium steels having vanadium, chromium steels having chromium, and so on. Non-ferrous alloys are alloys that do not contain iron as one of the components. The number of non-ferrous alloys used in technology is very large. Aluminium alloys like aluminium bronze, duralumin, and gamma alloy, along with magnesium alloys like magnalumin and electron, find numerous applications in various fields. Similarly, brass, an alloy of copper and zinc, and bronze, an alloy of copper and tin, are also important non-ferrous alloys. The table shown here lists some important ferrous and non-ferrous alloys along with their composition and uses. Potassium dichromate is one of the most important compounds of chromium. It is prepared from its ore, chromite. The preparation of potassium dichromate from chromite involves 3 steps. They are preparation of sodium chromate, conversion of sodium chromate into sodium dichromate, conversion of sodium dichromate into potassium dichromate. Let us see the process in detail. Finely powdered chromite ore is mixed with soda ash and then roasted in a reverberatory or rotating furnace in excess of air. The mass turns yellow due to the formation of sodium chromate. The sodium chromate solution obtained in the first step is filtered and treated with concentrated sulfuric acid and gets converted into sodium dichromate. On concentration, the less soluble sodium sulfate crystallizes out. This is filtered hot and allowed to cool, after which the orange-colored sodium dichromate separates on standing. A hot concentrated solution of sodium dichromate is treated with a calculated quantity of potassium chloride. Potassium dichromate, being less soluble, crystallizes out on cooling. Now, let us look at the properties of this compound. Potassium dichromate is a crystalline ionic solid with a very bright red-orange color. The chromates and dichromates are interconvertible in an aqueous solution, depending upon its pH. Even weak acids cause the yellow chromate to change into the orange dichromate, while it is reversed, adding an alkali or a carbonate solution. The structures of the chromate and the dichromate ions are given here. While the chromate ion is tetrahedral, the dichromate ion consists of 2 tetrahedrals sharing one corner with a CR-OCR bond angle of 126 degrees. Sodium dichromate is highly soluble in water and is widely used as an oxidizing agent. Potassium dichromate is preferred to sodium dichromate for use in volumetric titration. This is because the sodium compound is hygroscopic, while the potassium compound is not. Thus, potassium dichromate is used as a primary standard in volumetric analysis. In an acidic solution, potassium dichromate furnishes nascent oxygen. In other words, the dichromate ion accepts electrons and thus acts as an excellent oxidizing agent. For example, acidified potassium dichromate oxidizes ferrous sulfate to ferric sulfate, hydrogen sulfide to sulfur, halogen acids to halogens, and stannous salts to stannic salts. It also liberates iodine from potassium iodide. Let us now see some important uses of potassium dichromate. Apart from being used as an oxidizing agent, potassium dichromate is also used in chrome tanning in the leather industry. It is used as mordant for dyeing and in the volumetric estimation of ferrous salts, iodides and sulfides. Potassium permanganate is the most important and well-known salt of permanganic acid. It is prepared by fusing pyrolusite ore or manganese dioxide with caustic potash or potassium carbonate in the presence of atmospheric oxygen or any other oxidizing agent like potassium nitrate. The reaction produces dark green potassium manganate, which disproportionates in a neutral or acidic solution to give potassium permanganate. In the laboratory, potassium permanganate is prepared by the oxidation of a manganese 2 salt by peroxodisulfate. Industrially, it is prepared by the electrolytic oxidation of a manganate solution. In this method, the manganate solution is placed in an electrolytic cell provided with a rotating wire netting anode. An inlet pipe made of iron for the liquor acts as the cathode. The oxygen liberated at the anode converts manganate into permanganate. The purple solution containing potassium permanganate is evaporated under controlled conditions. Potassium permanganate then crystallizes out. Let us now look at the properties of potassium permanganate. Potassium permanganate forms dark purple, anhydrous, needle-like crystals that are isostructural with potassium perchlorate. It is moderately soluble in water. On heating strongly, it decomposes into potassium manganate, manganese dioxide, and oxygen according to the equation shown here. The structures of the manganate and permanganate ions are shown here. Both these ions are tetrahedral. Pi bonds are formed by the overlap of the p orbitals of oxygen with the d orbitals of manganese. Note that while the manganate ion is paramagnetic due to the presence of one unpaired electron, the permanganate ion is diamagnetic. Let's now look at the chemical properties of this compound. Potassium permanganate acts as a powerful oxidizing agent in acidic, alkaline, and neutral solutions. The effective equations in each of these media are given here. Let us see some important oxidizing reactions of this compound in each of these media. In an acidic medium, it oxidizes sulfides or hydrogen sulfide to sulfur, sulfur dioxide to sulfuric acid, sulfides to sulfates, nitrides to nitrates, arsenides to arsenates, oxalates or oxalic acid to carbon dioxide. Ferrous salts to ferric salts, iodides to iodine, hydrogen peroxide to water and oxygen. In a neutral or fairly alkaline medium, it oxidizes manganese sulfate to manganese dioxide in the presence of zinc sulfate or zinc oxide as catalyst. Potassium iodide to potassium iodate. Sodium thiosulfate to sodium sulfate. Nitrotoluene to nitrobenzoic acid. Let's now study the uses of potassium permanganate. Alkaline potassium permanganate is used in organic chemistry under the name of Bayer's reagent. Apart from being used as an oxidizing agent in the laboratory, it is also used in the volumetric estimation of ferrous salts, oxalic acid or oxalates, and hydrogen peroxide. Qualitative analysis for the detection of halides. Bleaching of wool, cotton, silk and other textile fibers. Decolorization of oils. The two rows of elements at the bottom of the periodic table constitute the F block elements. These include the 14 elements from cerium to lutetium, called the lanthanoids, and the 14 elements from thorium to lawrentium, called the actinoids. While lanthanoids are characterized by the filling up of the anti-penultimate 4F energy level, actinoids are characterized by the filling up of 5F energy level. These two series of elements are, therefore, called the inner transition elements. Since the D block element, lanthanum, closely resembles the lanthanoids, it is usually included in any discussion of lanthanoids. Similar is the inclusion of the D block element, actinium, in the study of actinoids. Since lanthanoids effectively have only one stable oxidation state, +3, they resemble each other more closely than do a horizontal row of the transition elements. The chemistry of actinoids, on the other hand, is complicated. The complication is partly due to the occurrence of a wide range of oxidation states, and partly due to their radioactive properties. Now let us first take up the lanthanoids. The electronic configuration of the lanthanoids is shown in the table. Lanthanum, the D block element preceding this series, has the electronic configuration of xenon core 5D1 6s2. We might expect that the 14 elements from cerium to lutetium would be formed by adding 1, 2, 3, up to 14 electrons to the 4F level. However, it is energetically favorable to move the single 5D electron to the 4F level. For most of the elements, except cerium, gadolinium, and lutetium, The reason why gadolinium has a 5D1 arrangement is that this leaves a half-filled 4F subshell, which gives greater stability. Lutetium has a 5D1 arrangement because the F subshell is already full. The lanthanoids are characterized by the uniform +3 oxidation state shown by all the metals. Next, we look at the atomic and ionic radii of these elements. The atomic and ionic radii are shown in the table here. You can see that the atomic radii exhibit a smooth trend across the series, with the exception of the element europium. Europium, because of its crystal structure, has abnormal atomic radius. The ionic radii of the trivalent lanthanoid ions, in contrast, exhibit a smooth decrease. In lanthanoids and their trivalent ions, the effective nuclear charge experienced by the outer electrons increases with an increase in the atomic number due to the poor shielding of the F electrons. Hence, a regular decrease in the atomic radius is observed with an increase in the atomic number. This steady decrease in size of the atom or an ion among the lanthanoids is known as lanthanoid contraction. Because of lanthanoid contraction, the sizes of the third row of the transition elements are very similar to those of the second row. Thus, the second and third rows of the transition elements resemble each other more closely than do the first and second rows. Thus, pairs of elements such as zirconium and hafnium, niobium and tantalum, and molybdenum and tungsten are almost identical in size. The close similarity of properties in such a pair makes chemical separation very difficult. Now, let us look at the oxidation states of these elements. The sum of the first 3 ionization energies for each element is given in the table. The values are low. Thus, the oxidation state of +3 is ionic, and the trivalent lanthanoid ion dominates the chemistry of these elements. The divalent and tetravalent lanthanoid ions that do occur are always less stable than trivalent lanthanoid ions. The oxidation numbers of +2 and +4 do occur, particularly when they lead to a noble gas configuration, a half-filled F subshell, a completely filled F subshell. An example of the first case is the cerium 4+ ion. Although cerium 4+ is favored by its noble gas configuration, it is a strong oxidizing agent, which is evident by the standard reduction potential value of the cerium +4, cerium +3 couple. Therefore, it reverts to the stable +3 oxidation state. In addition to cerium, neodymium, promethium, terbium and dysprosium also exhibit +4 oxidation state in their oxides. The best examples of the second case are europium +2 and terbium 4+. However, europium +2, being a strong reducing agent, changes to +3 oxidation state. Samarium, like europium, also exhibits both +2 and +3 oxidation states. Terbium +4, on the other hand, acts as an oxidant and gets itself reduced to +3 state. Terbium 2+ stand as an example of the third case. Terbium 2+ ion acts as a reducing agent and changes to +3 state. The important physical properties of lanthanoids are: all lanthanoids are soft and silvery white metals. The hardness of these metals increases with an increase in the atomic number. They are electropositive and therefore very reactive. They rapidly tarnish in air due to the formation of an oxide coating on their surface. They are good conductors of heat and electricity. Their physical constants, like melting point and density, change gradually, except in the case of europium, terbium, samarium, and thulium. Many of the trivalent lanthanoid ions are colored, both in their crystalline state and in aqueous solutions. The color of these ions is directly related to the number of unpaired electrons in the 4f subshell. The absorption spectra of the compounds of trivalent lanthanoid ions show a very sharp line band in the UV visible or near infrared region. These bands are due to internal electron transitions in the partly filled 4f shell and are called F to F transitions. Lanthanoid ions that have empty f orbitals, like trivalent lanthanum, half-filled f orbitals, like trivalent gadolinium, or completely filled 4f orbitals, like trivalent lutetium, are colorless. Due to the presence of unpaired electrons in the 4f orbitals, all lanthanoid ions show paramagnetic behavior with the exceptions of trivalent lanthanum and tetravalent cerium with F0 configuration, and divalent terbium and trivalent lutetium with F14 configuration. Paramagnetism is the maximum in dysprosium. The value of the first ionization energy of the lanthanoids is about 600 kilojoules per mole, and of the second ionization energy is about 1200 kilojoules per mole. These values are comparable with the values of the ionization energies of the alkaline earth metals, particularly calcium. A detailed study of the third ionization energy shows the extra stability associated with empty, half-filled, and completely filled orbitals of the F level. This is reflected by the abnormally low value of the third ionization enthalpies of lanthanum, gadolinium, and lutetium. Now, let us look at the chemical reactivity of these elements. The first few members of the lanthanoids are quite reactive and show chemical behavior similar to that of calcium. However, with an increase in the atomic number, they behave more like aluminium. The standard electrode potentials of the Ln+3 Ln couple indicate that all the lanthanides are more reactive than aluminium. Let us now look at some important reactions of these elements. These metals combine with hydrogen when heated gently in the gas and form hydrides of the type LnH2 and LnH3. On being heated, these elements combine directly with nonmetals and form carbides with carbon, nitrides with nitrogen, sulfides with sulfur, and halides with halogens. They liberate hydrogen from dilute acids. They burn in oxygen to form oxides of the type Ln2O3. They react slowly with cold water but more rapidly with hot water, and liberate hydrogen gas. The lanthanoid oxides and hydroxides are basic in nature, like alkaline earth metal oxides and hydroxides. Let us now look at the uses of lanthanoids. Lanthanoids are widely used for the production of alloy steels for pipes and plates. A well-known alloy, mish metal, which consists of 95% of a lanthanoid metal, 5% of iron and traces of sulfur, carbon, calcium and aluminium, is used in a magnesium-based alloy to produce bullets, shells and lighter flint. Mixed oxides of lanthanoids are used as catalysts in petroleum cracking. Some individual lanthanoid oxides, such as europium oxide and ytterbium oxide, are used to produce the red colors on television screens. The oxides of praseodymium and neodymium are used in glass, such as in television screens, to reduce glare. The 14 elements from thorium to lawrencium, in which the differentiating electron enters the 5f orbital, are called the actinoids. Only the first 3 elements, namely thorium, protactinium, and uranium, occur in nature. The other elements are made artificially by nuclear bombardment. All the actinoid elements are radioactive. The first few members have relatively long half-lives. However, the remaining members have half-lives ranging from a few days to a few minutes. Let's first look at the electronic configuration of these elements. The electronic configuration of actinoids is given in the table here. Since the difference in energy between the 5f and 6d orbitals is small for the first four elements thorium, protactinium, uranium and neptunium. The electrons in these elements and their ions may occupy the 5f or the 6d levels, or sometimes both. However, note that the filling of the f orbital starts only at protactinium and not at thorium. Later in the actinoid series, the 5f orbitals do become appreciably lower in energy. Thus, from plutonium onwards, the 5f shell fills in a regular way, and the elements become very similar. The irregularities in the configurations at curium and lawrencium are related to the stabilities associated with the half-filled and completely filled configurations. As 5f orbitals are not as deeply buried as 4f orbitals, the 5f electrons can participate in bonding to a greater extent. This explains the higher oxidation states shown by the earlier actinide elements. Now, let's look at the atomic and ionic radii of these elements. The atomic and ionic radii of the tripositive and tetrapositive actinoid ions are given in the table. As you can see, there is a steady decrease in the ionic sizes of the tripositive and tetrapositive ions. This may be referred to as actinoid contraction. Due to the poor shielding by the 5f electrons, the contraction is greater from one element to another in the series. Now, let's talk about the oxidation states of these elements. Unlike lanthanoids, actinoids show a variety of oxidation states. This is attributed to the small energy difference between the 5f, 6d and 7s levels. The oxidation states of these elements are given in the table. You can see that +3 is the common oxidation state of actinoids. The maximum oxidation state first increases up to the middle of the series and then decreases. That is, it increases from +4 for thorium to +5, +6 and +7 for protactinium, uranium, neptunium and plutonium, but decreases in the succeeding elements. Actinoids, like lanthanoids, have more compounds in the +3 state than in the +4 state. However, +3 and +4 ions in actinoids tend to hydrolyze. While lanthanoid ions do not. The important physical properties of the actinoids are: they are all silvery metals. They are highly reactive, especially when finely divided. They tarnish in air due to the formation of an oxide coating. Although paramagnetic, their magnetic properties are more complex than the lanthanoids and are difficult to interpret. The important chemical properties of the actinoids include: they react with hot water to give a mixture of an oxide and a hydride. They react readily with HCl, but its reaction with other acids is lower than expected. Most of them are slightly affected by nitric acid due to the formation of a protective oxide layer. They are basic and do not react with sodium hydroxide. They react with oxygen, the halogens, and with hydrogen. Since in both the series of elements, the f orbital is progressively filled, the two series of elements resemble each other. On the other hand, they also differ from each other due to the lower binding energies of the 5 f electrons in actinides than those of the 4 f electrons in lanthanides. The important differences between the lanthanoids and the actinoids are summarized in the table given here. Finally, let's look at the important applications of the D and F block elements. Iron and its alloy steel are used extensively in the construction industry. Titanium is used in aircraft and spaceship manufacture. Tungsten is used to make electrical filaments. Titanium oxide is used in the pigment industry. Manganese dioxide is used in dry battery cells. Zinc is used as the negative electrode in sealed dry batteries. Cadmium is used for alkaline nickel, cadmium storage batteries used in diesel locomotives, and also as the nickel rechargeable dry batteries used in radios and electronic appliances. Niobium alloys are used in jet engines. Tantalum is used to make analytical weights. Copper-coated steel is used to make copper coins in the UK. The copper-nickel alloy is used to make silver coins in the UK. Silver bromide is used in photography. Many transition metals and their compounds are used as catalysts in the chemical industry. For example, vanadium pentoxide in the oxidation of sulfur dioxide in the manufacture of sulfuric acid. Ziegler natter, a complex of titanium tetrachloride and trimethyl aluminium, in the polymerization of ethene to polythene. Iron in Haber's process for the production of ammonia. Nickel in the hydrogenation of fats. Palladium chloride in the Wacker process of oxidation of ethene to ethanol. Nickel complexes in the polymerization of alkynes and other compounds such as benzene. Here are some applications of F block elements. Alloys of lanthanides, known as mish metals, are used for the production of heat-resistant and instrumental steels. Borides, carbides, and nitrides of lanthanides are used as refractories. Lanthanide oxides are used as abrasives for polishing glass. Thorium is used in the treatment of cancer and in incandescent gas mantles. Uranium is used as a nuclear fuel. Plutonium is used in atomic reactors and in atomic bombs.